In this unit, we'll be doing a math review of concepts that you'll need to know how to use in order to solve dynamics problems throughout this course. We're going to start by taking a look at solving two equations with two unknowns. This is one of the most common type problems that you will encounter in this course. So looking at page 15 for example 1-4, our two equations are as follows. Equation 1 is 3x plus 4y equal to 8. And equation 2 is 6x plus 2y equal to 10. Now there are two methods that we can apply to solve this type of problem. In method 1, what we're going to do is we're going to try to simplify or subtract out one of the unknowns. So if we take equation 1 and we multiply that by -2, we get -6x minus 8y equal to -16. Then we simply add that to equation 2, which is, again, 6x plus 2y equal to 10. So when we add these up, we get -6, -6y, and of course 0x. So if we divide now each side of the equation by -6, we end up with y equal to 1. So that solves our first unknown. Using y equal to 1, we're going to sub that into our original equation 1, which is 3x plus 4y equal to 8. So 3x plus 4 times 1 equal to 8. 3x plus 4 equal to 8. So I'll bring the 4 to the other side, and we get 3x equal to 8 minus 4. Now we get 3x is equal to 4, and now we divide both sides by 3. So x is equal to 4 over 3. So our final answer would be x equal to 1.3. That should be 1.33. Okay, so there's our answer for those for x and for y. That's using one method. A second method is as follows. So that was method 1. So we're on method 2 now. In this method, what we're going to do is I'm going to start again with equation 1. Now I'm going to solve just for x with this first equation. So what I mean is I'm going to take 3x equal to 8 minus 4y. And then I'll divide both sides by 3. So I get x is equal to 8 minus 4y over 3. If you look, we have equation 2, which is 6x plus 2y equal to 10. So now what we would do is we would take what x is equal to, and we would sub that right into here. So what you would have is 8 minus 4y over 3 plus 2y equal to 10. And so now we have that one equation with one unknown, with y. Now, this method in this particular case does look like it gets a little bit messy because we'd have to multiply the 6 into those two different terms and start simplifying. And so for this particular case, it is a little bit messier, a little bit more difficult, but there are many instances where using method 2 is quite advantageous, especially if we do have, for example, some of the knowns, or we can get one of the unknowns through other means, then we just sub it back into this equation. So I just want you to be aware of both of these methods when solving two equations with two unknowns. Okay, so moving on, we have the quadratic equation or quadratic formula. X is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. A quadratic equation is used to solve problems that typically look like as follows. So we would have a x squared plus b x plus c equal to 0, where each of those constants, a, b, and c, have a specific value. So this is a general form. So let's take a look at example 1.5. In this problem, we have 5x squared plus 12x minus, not plus, we have 12x minus 2 equal to 0. And so this is the general form where our 5 is the a constant, 12 is the b constant, and negative 2 is the c constant. Okay, so a equal to 5, b equal to 12, and c equal to negative 2. So if we use these constants, we can then solve using the quadratic formula. So x is equal to negative 12 plus minus the square root of b squared, which is 12. So 12 squared minus 4a, which is 5, c, which is negative 2, all over 2 times a, which is 5. Now you see that we have plus minus. That means that this is actually two equations shown in one instance here. Technically what that is x is equal to negative 12 plus the square root of 12 squared minus 4 times 5 times negative 2 all over 2a. And it is also x equal to negative 12 minus the square root of 12 squared minus 4 times 5 times negative 2 over 2. So I had a, which is 5. So I can replace the a on the left-hand side there with 5. Okay, so that's really what this equation is doing, is we're solving two different equations. So we're going to get two values for x. X is equal to negative 12. That's why I like to actually, instead of breaking it up so early, we can simplify first. So I can say negative 12 plus minus the square root of 144 plus, because we have a negative 4 and a negative 2, so it ends up being a positive number. So plus 40 all over 10. And then we have x is equal to negative 12 plus minus the square root of 184 over 10. Okay, and then from there, you can go ahead and solve for both values. So we would end up with x is equal to negative 2.56, or we end up with x is equal to 0.156. This is used typically for parabolic trajectories of projectiles. So that is a topic that we do cover in this course. And really all it's doing, you may remember this from math, where we have, so if I just draw out an axis here, so I have an x-axis and a y-axis. And if you were to draw a parabola might look something like this. So this equation is a squared power equation, as we see with the x squared all the way over here. So this x squared plus x, so ax squared plus bx plus c. Takes the form, this type of object in math takes that type of equation, that form of an equation. And so all we're doing here is actually solving for the 2 points at which this parabola crosses the x-axis. Okay, so in this particular case, we ended up with negative 2.56 and 0.156. So this parabola would actually be shifted to the left of the origin since we have a negative value. That's all that this is doing. But it's really helpful when we're trying to solve, as I said, projectile problems where you say you're throwing a ball in the air. It follows this sort of path. And that's why you end up using this equation often when we cover that topic. Another one here, example 1.6, that's 3x squared minus 5x plus 1 equal to 0. Again, the first thing that you want to do is figure out what the a, b, and c constants are. So a is equal to 3, b is equal to -5, and c is equal to 1. From that, it's helpful to just write out your quadratic formula. So that's x is equal to -b plus minus the square root of b squared minus 4ac all over 2a. So I'll let you go ahead and try out this problem. Again, you're just going to sub these constants into this equation, and you are going to get two values for x. So for this one, you should get x is equal to 1.43. You should also get x is equal to 0.232. So again, that is where that parabola crosses the x-axis at those two locations. So take your time. You'll be using, you are allowed a calculator throughout this course. So take advantage of that and just practice this, right? You want to make sure that you feel comfortable being able to solve this problem. Okay, moving on to some trigonometry, specifically with right angle triangles. This gets particularly important when we start dealing with planar motion later in Module 1. So if we look at page 19, I'm going to start by just drawing out an axis here with a right angle triangle. Okay, so here's our triangle. I'll show the right angle there. And typically this is given an x, a y, and an h for hypotenuse. And we typically either have or need to find an angle, and we'll call that theta. So you may remember from high school the saying SOHCAHTOA, okay, for trigonometry. So what this is referring to specifically is our sine, cosine, and tangent. So for the first one, sine, that's opposite over hypotenuse. So sine theta is equal to opposite over hypotenuse. Cosine theta is equal to a, so that's adjacent, that's the ca, adjacent over hypotenuse. And last but not least, we have tan theta is equal to, that would be opposite over adjacent. So if we're applying these equations to that figure there on the right hand side, then that really means that sine theta, for the value in order to solve for theta itself, we need to do opposite. So that's opposite to theta would be y over hypotenuse, which is h. For cosine theta, that's adjacent. So that's the one basically touching it. So that's x over hypotenuse. And last, we have tan theta, which is equal to opposite. Again, that's y over adjacent, which is x. Okay, so when you are given right angle triangles, often we need to either find one of the lengths, x, y, or h, or we need to find theta. Now, one thing that you don't want to forget either is that's easy when you have an angle, but perhaps you don't need to find an angle, you just need to find one of the sides. Well, we can use the equation h squared is equal to x squared plus y squared. And this is what we call the Pythagorean theorem. Okay, so let's look at example 1.7. So this is on page 19. We are given a right angle triangle, and we have the values 30 degrees for the angle there. We have 4 inches on the side, and we need to solve for side A. So we want to, of course, determine length A. You can go back here and look at basically with what's given, which one of these can we use? Okay, so if we look at, for example, sine theta, that would be y, that's opposite over hypotenuse. Sine theta is equal to opposite, which is A over 4 inches. So if we sub in our values, we get sine 30 degrees is equal to A over 4. So in order to solve for A, we need to multiply both sides by 4. So A is equal to sine 30 degrees times 4. So if you punch that into your calculator, you should get 2. Anytime you're solving a problem, you should be carrying through your units all the way through. If you don't, it's not the end of the world as long as the final answer includes the units. If the final answer does not include the units, and you're submitting that for an assignment or a test, then the final answer is considered incorrect. Okay, for triangles that are not right angles, we have the sine law and cosine laws that we can use in order to solve for either a length or an angle in that triangle. So if I were to draw out a non-right angle triangle, sides A, B, C, with angles, okay, then we can apply the equation shown here, and this is the sine law. So with this one, you see there are 3 terms, and you don't have to solve both of these equations simultaneously. In fact, what you can do is you can break this up so that you're just solving 2 terms at a time. So I could take, for example, the first 2 terms, or I could take the last 2 terms, or I could take the first and the last term to solve. The difference between the sine law and the cosine law is what's given in this triangle. As long as it's a non-right angle triangle, you will use either the sine law or cosine law to solve for a length or an angle. It just depends on what's given. Typically, you're using the sine law if you have a length with an opposite angle given. Whereas for the cosine law, typically you might have an angle, but you don't have the opposite side length. I'll show you what I mean here. So you can see, for example, in this particular equation, we are solving for C, and we're given the opposite angle in this case. We would have to be given the opposite angle. But we don't have any lengths with opposite angles. This will make more sense when we look at this example, particular example 8, So in this problem, we have a triangle that looks something like this, where we have 4 feet on the side, we have C, and we have 6 feet here. And then inside, we have an angle of 20 degrees, but we don't have the other 2 angles. Okay, so what we want to do in this problem is we need to solve for C and for theta. So we see that it's a non-right angle triangle. So immediately we think, okay, we have to use either the sine law or the cosine law. So I always start by looking at how we can use the sine law. So if we were to use what's given here and draw out the equation, write out the equation, we would do something like this. C over sine 20 degrees is equal to 4 over sine alpha is equal to 6 over sine theta. So the first thing to note is that the lengths are on top and the angles are on bottom, and the angles that you're using are opposite to that length. If we were to take any one of these any one of these equations within the sine law here, you would see that we have too many unknowns, right? Because we don't have a set of a length and an opposite angle that's given. So we can't use the sine law here. There's just no way to solve this. So instead what we're going to do is we are going to use the cosine law. C squared equal to, which we don't have, we're going to use the two lengths. So that would be 4 feet squared plus 6 feet squared minus 2 times the first length that we use times the second length that we use. Cosine, this has to be the opposite angle to the length we're trying to solve, which is 20 degrees. So you can see we can solve for this because the only unknown is C. So when you work that out, you get C is equal to 2.6 feet. So that gives us a value for C, which is one of the unknowns, but we also need to solve for theta now. Now that we have a length with its angle that's opposite to it, we can now plug this value into the sine law above and solve for theta. So I'm going to use that first term, and I'm going to use the third term in the sine law, and I'm going to solve for it. So using the sine law, I'm going to say that 2.6 over sine 20 degrees is equal to 6 over sine theta. I want to solve for theta. So I basically need to rearrange this equation so that I can solve for theta. So if I were to do that, I should get sine theta is equal to 6 feet times sine 20 over 2.6. And then we plug that into our calculator. Since we're solving for theta, you have to invert that sign on the opposite side there. And if you're not sure how to do that, please let me know, so that we get an angle of 52.1 degrees. Okay, so moving on, we're going to look at page 23. On this example, what we're going to do is I'm just going to draw out 2 lines here. Okay, and we have angles in here. Okay, so A, B, C, and D. So anytime you see a geometry like this, the opposite angles are going to be equal to each other. So that means that A is equal to B and C is equal to D. Similarly, we're going to draw out another triangle, non-right angle triangle here. And we have A, B, and C angles. We know that A plus B plus C is equal to 180 degrees. So if you have two, you've used the sine law to solve for 2 of the angles, then you can easily solve for the third angle, knowing that all 3 of them have to equal 180. Okay, so we're just going to draw a line and a line. So in this case, we have A and we have B. We also know that A plus B in this case is 180 degrees. Again, similarly, if we have a 90-degree quadrant that we're dealing with, and we have a line off here, and we have an angle A and an angle B, we know that A plus B 90 degrees here. Okay. Another really important one has to do with say I have 2 lines like this that these lines have to be parallel to each other. And then we have another line that bisects both of them. So what we're going to do here is I'm going to draw in some of these angles, just like the first one right over here on this slide. I said that these opposite angles are equivalent. So that works here as well. Okay, we can say that A is equal to C, and we can say that B is equal to D as well. Also in here, you're going to see, for example, that if I were to just draw out here the inner, okay, it looks something like this, with the angle C and the angle B in here. I've just kind of cut out the rest, cropped the rest out of there. This is what you would call the Z law, and it requires that, of course, these two lines are parallel, which in that previous diagram here, we see that that is the case. So what that means then is that C must be equal to B as well. Okay, so that's another one that you'll need to look for. And since A equals C and B equals D, we also know that C equals B. Therefore, A equals B equals C equals D. Okay, it might not be completely obvious when you first look at this, but when you break it down into these requirements, that does make more sense, right? Okay, one of the last sections here, similar triangles. So two triangles are similar if they have the same shape, but not necessarily the same size. This is true if one of the two following conditions are valid. The first, the corresponding angles of similar triangles are equal, or the corresponding sides are proportional. So what I mean by this is, let's say we have a triangle like this, and we have a triangle like this. Okay, are these triangles equivalent? No, but they may be considered similar triangles. And that's true if one of the two conditions are correct, meaning that if our angles here, so alpha, beta here, are equivalent. So if these are equivalent, then these are what we call similar triangles. The other thing that makes it, we'll use some Christmas colors here. We go A, B, C, and then A, B, and C. Clearly, the lengths are not equivalent here, right? So what I'll do, in fact, I'll call this A prime, B prime, and C prime, just so that we're not saying that these lengths are equal. They're clearly not equal. If I were drawing these triangles out and this is to scale, then they're clearly not equal. However, if you were to take the ratio of A prime to A, and let's say that it is exactly 2. We got a ratio of 2. It's 2 to 1, right? 2 over 1. And we looked at the other one, so B prime over B, and it's equal to 2, and C prime over C, and it's also equal to 2 to 1 ratio, then again, they would be considered similar triangles. And that's really important because you may come upon this during your studies in this course, where you have two triangles that look the same, and they are essentially the same if they're considered similar triangles if one of these two conditions are true. And then it allows you to very quickly and easily calculate the lengths. For example, if you know that A prime to A is a ratio of 2, and let's say we know the length then of B prime is 4, but we don't know what the length of B is, well, since it's a 2 to 1 ratio, we can easily calculate that. We know that then that if B prime is 4, then B is 2. Okay, you can also look to page 26 for more practice problems on this.